Good morning. We finished the previous lecture by talking about Lewis structures, and today we will continue developing that concept by talking about formal charges in Lewis structures. Although all the molecules that we drew last time were neutral, that doesn't necessarily have to hold true for any given molecule. So some molecules will be charged, they will have excess positive or negative charge in them. Or furthermore, some molecules, while they remain neutral, will have parts of them which will be excess positively or excess negatively charged. To look at a simple example of this concept, if you just look at a water molecule reacting with a proton, it will give a hydronium ion, which now has three protons attached to oxygen, and oxygen is positively charged. And so what we say here is that the oxygen has formal positive charge of +1. Now the question is, how do we determine formal charges in some sort of a systematic fashion? And the first thing that we do is count non-bonding electrons on a given atom. And we'll label this number as NB. The second thing that we'll proceed to do is count 1/2 of bonding electrons. And we will label this number as B/2. And finally, we will subtract the sum of the two numbers we just got. So subtract NB plus B/2 from the number of valence electrons. And we'll label this number as V. So this will now yield the formal charge on an atom. So formal charge equals V minus NB plus B/2. Let's look at how this applies to some relatively simple examples. So one of the molecules we'll look at is methane. Its formula is CH4. So this is methane. And we can look at both hydrogen and carbon in this molecule. So if we start counting each one of these numbers, number of bonding electrons for each hydrogen is just 1, whereas for carbon it's 4. Neither of them has non-bonding electrons, so these are both 0. Hydrogen is in the first group, whereas carbon is in the fourth group. And if we start subtracting the sum of this and this from this, we'll get a 0 here and a 0 here, which means that both hydrogen and carbon in methane have no formal charge to them. Let's look at an example now which does have a formal charge, and that is related a molecule in terms of molecular shape, which is basically ammonium ion. Now if you look at the same numbers, CV, NB, NB 1/2 for hydrogen and nitrogen, hydrogen is still in the first group, but nitrogen is the fifth group. Number here is 0 and 0 here, 1 and 4. And so what we get for hydrogen is 0, but for nitrogen we get +1, which means, as I drew it out here, that nitrogen does have a formal positive charge on it. Let's look at an example. It's a little bit more complex in that it has 3 different elements. This, as we will learn later on, is nothing else but a protonated formaldehyde. And for simplicity's sake, we can skip hydrogen here, which clearly has no formal charge. But if you look at oxygen and carbon, then we will see that oxygen is in the 6th group, whereas carbon is in the 4th group. In terms of non-bonding electrons, carbon has 0, oxygen has 2. In terms of bonding electrons, carbon has, again, 4, whereas oxygen has 3. And the sum of these two numbers is 5, and 6 minus 5 is 1. So that means that oxygen has a formal positive charge, whereas carbon charge is 0. So this is how the concept of formal charges applies. Now, we don't have to go through this analysis every single time. Since there is a fairly limited number of different elements in organic compounds, actually just a handful of them, it is easy to make generalizations in terms of formal charges. So if you look at the elements that show up in organic compounds commonly, such as boron, carbon, nitrogen, oxygen, and halogens, where this can be fluorine, chlorine, or bromine, or iodine, then let's look at first at their valence numbers. For boron it's 3, for carbon is 4, 5 for nitrogen, 6 for oxygen, and 7 for these. And in neutral compounds, boron will have 3 bonds to it and no free electron pairs. Carbon will have 4, nitrogen will have 3, but it will have an electron pair. Oxygen will have 2 and 2 electron pairs, whereas the halogen will have 1 bond and 3 electron pairs. This is what happens if we observe these elements in their neutral state. If they're positively charged, if they're negatively charged, they're anionic, then boron will indeed have 4 bonds to it and will be negatively charged. Carbon will have 3 bonds and a free electron pair. Nitrogen will have 2 bonds and 2 free electron pairs. Oxygen will have 1 bond and 3 free electron pairs. And the situation with halogens is interesting because we cannot have obviously an anionic halogen in a organic compound, since such halogen has no chemical bonds to it, so it's a free ion. Now if you're going to talk about cationic species, cationic boron is actually very uncommon, so you can just skip that. Cationic carbon would have 3 bonds, but no electron pair here, so it will be positively charged. Cationic nitrogen would have 4 bonds to it. Oxygen will have 3 bonds and only 1 electron pair. And a halogen would have 2 bonds and 2 electron pairs to it. Okay? Now, the important thing about formal charges is that they have to coexist together with the octet rule. So if we look at a molecule, hypothetical molecule that is drawn like this, it could be tempting to see this positive charge on nitrogen and negative charge on chlorine simply attracting each other and forming a bond, which means that we would get a structure that looks like this, and that is technically neutral. The problem here is that this is incorrect because there are 5 bonds to nitrogen. And what this means is that nitrogen has 10 electrons in its valence shell, which is just too much. It has to have 8, otherwise it starts filling up the next shell, and that is not so stable. So this, in such a case, would be a correct structure.